Welcome to episode 9 of the Shader Dev series. Today we will be talking about one of the more complex topics that we've ever covered or will cover in the entire series, and that is the bump map and shader. This tutorial will be supplemented by smooth jazz music from the bar across the street, because there's nothing I can do about it. So before we get started, let me take you on a journey into the past. When 3D graphics was first in its infancy, people wanted to apply interesting textures to their 3D surfaces. However, they were limited in how they can do this. For example, typically each polygon had to be one flat solid color, and in order to obtain something more realistic, or to render something more realistic like this pattern we have here, somebody would have to essentially draw many polygons, each of them at different colors. And to obtain a rather complex surface like this, they had to draw hundreds of thousands of polygons, each one at a different color. In other words, doing it this way was naive and basically infeasible for the graphics hardware at the time. So somebody came up with this interesting idea. Well, instead of drawing different polygons, hundreds and thousands of different polygons of different colors, why don't we consider mapping an image onto the surface? And basically texture mapping was born. The interesting thought or process behind texture mapping is it is always cheaper to shade pixels or to do interesting calculations in pixels than it is to do those by increasing the number of faces. So you always want to shade pixels. You don't want to add more polygons. More polygons hurts performance. This example right here is probably somewhere around 100,000 polygons, where this one is just a single polygon. The difference being this one is, the difference here being that we're using a texture map on the single polygon being drawn. So taking this concept a little bit further, when you're drawing something that is flat, like lava, I guess, the effect looks decent, but when you start looking at objects that were intended to have a little depth to them, from grazing angles, they start to look a little less realistic. For example, the whole point of a texture map is to make the surface look realistic and to save on polygons by using an image instead of drawing many polygons to basically mimic the same amount of detail. However, when you want to draw something like bricks, you'll notice that the effect kind of gets destroyed when you look at it from grazing angles, and all that fine detail seems to get lost. So, why do we texture map? If you guys remember from one of my earlier videos, I had an example where I showed light striking the surface and then scattering in various different directions. But I didn't talk about the color of the light or the color of the reflection. Real life is more like this. If you have white light striking a green surface, the green surface properties will cause it to absorb all of the bandwidth or all of the spectrum colors of light with the exception of green and reflect green. So it'll absorb all of the colors red, blue, yellow, violet, and it will reflect green and make the surface appear green because the reflection color to the eye, what you see, is the reflected green light. Taking that one step further, why do we use texture maps answers that question in regard to if we want to have different color properties at different positions or different points on the surface, we allow that texture map data or texture color to affect the material color at a certain point on the property or a certain point on the surface. So that when the light strikes the surface in one spot, you might get one color, but if the light strikes the surface in a different spot, you might get an entirely different color, which is basically what the texture map provides for you. Now, what is bump mapping, or where does that come in? Essentially, in the example I showed you before, the normal of the surface is used to calculate the lighting, and that normal is essentially calculated once for the entire polygon. It's perpendicular to the flat polygon surface, and that's it. And that normal is used to tell you what the light reflection property should be, or how the light should reflect off of the surface. Now, the normal is the same no matter where you strike on the surface. No matter where the light strikes on a truly flat surface, the normal vector won't change. However, if we decide to expand upon this concept and implement what's called a bump map, we can use the pixels in the bump map to essentially provide different normal vectors facing in different directions depending on where the light strikes the surface. This is essentially the core concept of how bump mapping works. And in theory, or on slides, it's simple, but in practice it gets a little complicated. For starters, if you guys remember the surface local space that I was talking about back in the transforms video, this space now becomes critical for bump mapping because in order for us to work in a bump map space, we have to work in the surface local space so that we can find out where we are with respect to the rest of the surface. So now instead of the shader needing just a normal vector to work, it needs a normal vector but also the two other axes of its local coordinate system, namely the tangent vector and the cross product of the tangent vector and the normal vector, which is also called the binormal. So in short, the normal, the tangent, and the binormal. Those three vectors are needed to perform bump mapping. So here's the part where I come in and tell you guys that we are approaching the limit of some of my understanding of some of these concepts, in the sense that I'm not an expert on bump mapping and I'm going to do the best I can to explain it, but I might not get it perfect. So there are a lot of other shader programmers out there that are a hell of a lot better at this stuff than I am. And I'm sure they could probably walk you through every aspect of how a bump mapping shader works and even recall it from scratch and memorize it. I'm going to do the best I can. However, I've only really figured out how to do bump mapping like last year. So we're going to see how I do here. I'm going to pull up Vertex Studio, and I'm going to go ahead and get out a keynote here, so I don't need it. And what we have here is essentially a texture-mapped brick surface, which is okay, but is not, like I said, realistic looking at grazing angles. And it's also not very realistic when you see the light move around it. It almost looks like somebody painted a picture of bricks on a very shiny table or a very shiny surface, which is not, it doesn't look like real bricks. Let's put it that way. So in order to combat this, we are going to implement bump mapping. Now I could be a turd and I could cheat here and I could just switch this to the built-in bump map shader in Vertex Studio, but we are not going to do that. What we are going to do instead is type bump to make our own bump mapping shader. Something I was going to do here. Oh, so this is important. We can't do bump mapping without a bump map. It's not some magic texture map that just comes out of thin air. We have our diffuse map here, which is also just called your normal color texture map. But we need a special map called a normal map to do this, for it to work. Lucky for us, I found a program on the web that does exactly this for us called Crazy Bump. And we are going to use Crazy Bump if it would fit on the screen. So Crazy Bump works by taking a picture and generating normal maps from it. It's not as perfect as if the normal map was generated via other means, but it does pretty good for anything that I've tried to do it on. So I'm going to go ahead and find the brick texture that I used for my diffuse, and I'm going to provide that as input into Crazy Bump. Now you'll notice that normal maps kind of look blue, and that's because basically what they do is they encode normal vectors into image data. So XYZ becomes red, green, blue, or RGB, and Z being the component that is the up direction off the surface. And since most normal vectors, or most vectors shoot directly off the surface, directly up, that Z component is going to be larger than the X or Y, so that means the blue is going to be the largest. So that's why most normal maps actually look blue. So what I'm going to do here is once again pull this ridiculous technique to see if I can save this. Alright, it's this one right here. So I'm going to try to save. Okay, so I'm going to go ahead and import the normal map just to have it, this is the wrong thing, into my scene, like so. Now we have our normal map, and we can start working on our shader. So I'm going to go into the shader code here, and like I said, I do not have memorized the technique for bump mapping. Unless you guys want to watch me trial and error for like an hour, what I'm going to do is I'm going to load the bump mapping template that comes with Vertex Studio, and I'm going to walk you guys through how it works. So there's a couple things we need to do to basically pull off bump mapping. The most important thing is now, In the past, our lighting calculations were done in view space, or eye space. In a bump mapping shader, we find it's more convenient to work in world space. So we've set up some transforms that basically make doing that a little simpler. For starters, we provide some extra information to the vertex shader that's needed to enable us to do that. Namely, we provide the tangent alongside the normal so that we can basically build our surface local coordinate system out of the normal and the tangent, and then the binormal, which is made up out of the cross product of the normal and the tangent. Not directly provided because it's actually faster and easier to compute it than it is to provide it and waste GPU memory to do this for every single vertex. Basically, provide you a surface local coordinate system vector that can be used to operate within the surface. So I'm going to show you what one of these look like by turning it on. I'm just going to go to Object, Generate Tangents, which it looks like I just turned off because I'm stupid. Let's put that back. And then I'm just going to show the normals here. And you can see at every single point there are now 3 vectors. It's really hard to see here, but basically there is a blue one, which represents the tangent. There is a green one, which represents the binormal, and then there's the red one, which represents the standard normal. And these 3 things make up your surface local coordinate system. And in order to use these in the shader, all you basically have to do is declare tangent. So now that you've got everything set up, let me try to walk you guys through what this crazy bump map shader does, or at least the vertex shader. It's important to basically take the normal vectors that have been digitized or that come with the bump map and to transform those into world space so that we can use them for lighting calculations. And the way that we do this is we build a 3x3 matrix transform which basically transforms from surface local, which is the coordinate system that the normal map vectors are in, to our world space. Now, I'm not an expert on this. From what I understand in linear algebra, the way that you transform between coordinate systems that have axes provided is that if you make up the matrix that performs the transform for you by using the axes, or sometimes called the bases, the orthogonal axes of the coordinate system that you want to transform into, if you build the columns of your matrix, your 3x3, out of those axes, that magically or miraculously is the transform that you wanted or needed. And basically what we're doing here is building that transform. So when you see that I'm actually assigning the 3 columns of surface to local world there, I'm basically building that transform. It is hard to explain this stuff, so I'll try to go slow. Basically, the transform is built by using the 3 axes of the coordinate system that I'm trying to go to. The x-axis being the transform of the tangent vector into world space, and that's done by the model matrix, which goes from model space to world space. The second part is probably the most confusing line in the entire shader, and it is extremely hard to explain, but basically it's the same thing that normal matrix does to the normal. If you want a normal matrix to be transformed, for some magical reason, you always have to transform it by the inverse of the model matrix, and not just the inverse of the model matrix, but what's the word I'm looking for? Transpose of the inverse of the model matrix, which is the equivalent of multiplying it on the right. It's the best way I can explain that. That's how you get the normal vector, or the z-axis, for your local surface to world space transform. Once you have those 2 axes, you get the binormal simply by doing the cross product of the other 2, and that will give you the axis you need. Note that z corresponds to the normal shooting off the surface, which is why the surface local coordinates given to you by the bump map are mostly blue when you look at them in color form. Once you have your local surface to world transform matrix, you pass that as an output. The entire thing gets interpolated as an output of the vertex shader and an input to the fragment shader, which actually does the bump mapping work. After that, we get the world space position, which is easily obtained by transforming the model or the position by the model matrix. And after that, I just realized after going through this so many times, this is wasteful. It seems that I'm recomputing VA normal, which again is the normal matrix times the normal, which is also the same as multiplying the normal by the model matrix inverse. If I had understood this better when I wrote this shader, I probably wouldn't have done that. The TC is just the texture coordinate times bump scale. We're going to leave bump scale as 1 for this example. And then finally, the position is equal to the model view projection matrix, or the position transformed by the model view projection matrix, which is something every vertex shader has to do. Nothing new there. It's a lot of stuff. The fragment shader, luckily, is not as, it's equally as complicated, I'm not going to lie to you. So we declare some inputs, namely to get the world space normal. And then we bring in the texture coordinates. And of course that local surface to world transform, which is needed for us to transform local surface local space vectors into world space vectors. And lastly, the VA position. So I'm going to go ahead here and I'm basically going to keep going. So I'm going to look at the uniform variables. The uniform variables are basically exposed as structures that are defined by Verto Studio System. These are, again, system uniforms. I haven't really covered them too much. The first one is just gives you the diffuse color is set by the editor. So the diffuse color of the surface that I set in the editor. And the light structure gives you the world position of the light, which is important because we are working in world space now. If you want more information about these system uniforms, like I said, that's all in the shader programming guide of Verto Studio. So I declare an array of lights. I'm only using one, and that is automatically set for me by the system to the correct light. So when we actually look at the body of the fragment shader code, which actually does the bump mapping magic, we start out by just applying a texture color to basically be just white, because to show this example off, I want to show just only the bump map part and leave the texture off for now. This is the important part where we retrieve the encoded normal from the bump texture. So we actually access the bump texture here, which is a special texture map that contains the surface normal, or the surface local normal encoded in an image. And that next line, local chords, is basically set equal to the special code that is, this is the way to do it, to get a normalized vector that has been encoded in an image. Because images, red, green, blue, can only go from 0 to 1. Normals, of course, at least unit normals, can go from -1 to +1. So this little calculation right here just takes care of that for you. It basically shifts everything over and retrieves the local coordinate, the local normal in the right format. This next part here is the important part. We actually apply the local surface to world matrix, or transform, into the local coordinates. And basically what this does is it transforms that normal that came from the file from surface local space to world space, which is what we are working in. And that is basically what kind of rotates that special normal and aligns it with the surface, which is, you know, what we're working with. It basically aligns that normal to the actual surface that we're shading. It's important. It's very confusing, but that line is probably the most critical part of the whole bump mapping shader. Once we have that, we basically have our world space normal, and we can obtain a vertex to light source vector, which is, like I explained in the vectors video, if you want a vector, you just basically subtract what you're aiming to minus what you're aiming from, and you have your vertex to light source. The light direction is basically the normalization of that vertex to light source. The diffuse color is just the material diffuse, which just comes in from that uniform struct. And this whole thing boils down to, at the end, the same n.vp calculation, where we take our world space normal and dot product that by the light direction vector, and then we have our entire lighting calculation done with bump mapping turned on. So once I build this shader, I'm going to show you guys essentially what this looks like. Enough talking about it. If I hit build and I set the texture equal to the right texture, and I set the bump scale equal to something that's not 0, so it makes sense, you will see that we basically have some bumps. Now it looks like we're basically just applying a gray texture to the surface, but that's not what's going on. The surface being shaded here is still completely a solid gray surface, but what we've done here is we've affected how the lighting strikes the surface. Now, let me make sure I didn't get this flipped. I didn't. So what I'm making sure here is that when I move the light around, the bumps on the surface respond properly. Namely, I want those highlights on the lower left to be bright and on the upper right to be dark of the bricks. It's a way to test that you got your bump map not flipped. So basically, that's how bump mapping looks. It looks pretty neat when we don't have the original texture applied, but it looks really cool when we turn the original texture back on. So I'm going to go ahead and pull the texture from the diffuse color, which is the normal texture map, back in. And now what we have is something that looks far more realistic than what we started with, which is basically bump maps on a texture map surface. And as you can see, it responds quite nicely when I move the light around, and it looks realistic. It no longer looks like we've painted a brick mural on a flat, piece of paper or glossy piece of paper. It looks like, much more like realistic bricks. So that's basically our bump mapping effect, and that's the bump mapping shader. And this starts to show you how you can really pull a lot of these concepts together to implement some really crazily awesome realistic effects. And it gets even better. If I go ahead and switch this to my more advanced built-in bump map shader, which supports specular highlighting, now I notice that it actually honors the highlight color that I've set in here. And when I move the light around, it looks almost like it's been raining on the bricks, and they start to look really realistic. So that kind of shows you how bump mapping can really add some realism to your scene. So I'm probably running over like I usually do, so I'm going to go ahead and end here. That is the bump mapping shader video, episode 9 of the shader programming series.